How many different 10-digit numbers can be made with the digits 1, 3, 4, 6, 8, 8, 5, 0, 5, and 5 that are smaller than 5 billion? Well, the first thing to consider here is the first digit in the sequence. So since it's smaller than 5 billion, we know that it can't start with anything that's 5 or greater. So you would start writing those down. So there's 1, 3, 4, and 0. However, as some of you might have figured out, you obviously cannot start a number with 0. So that's crossed out as well. So there are 10 digits. Let me just write out the lines here. A little bit messy. So we've determined that there can only be 3 options for the first one. So let's say it's 1, for example. That would leave us with 3, 4, 6, 8, 8, 5, 0, 5, and 5. So those make up 9 digits. So it's 9 factorial. However, we can't just stop there because obviously there are some groups. So there are 3 5s, and there are also 2 8s, which means we need to plug these in under the 9 factorial to ensure that we get the proper answer. Because obviously having an 8 switch with the other 8, quote unquote, wouldn't make any actual difference to the number. However, this isn't all the equation is. We also need to put the 3 and multiply that. So then if you were to punch all this into your calculator, you would come out with an answer of 90,720 different ways that you can make a digit that's smaller than 5 billion with these digits up here. Next, imagine that this is the first half of a very long license plate. Without using I, O, E, or L, how many license plates are possible with the original numbers, these ones up here, and a 5-letter combination following, assuming you cannot use the same letter more than once? Now this question says basically that we're going to find a 5-letter combination to put after the numbers before. So it doesn't actually affect this equation in any way, it's more so just something afterwards. So the first step is to determine how many different possibilities we have per spot. So the first one is going to be 22, because obviously there are 26 letters of the alphabet, but we have taken out I, O, E, and L. So then, if we use 22 for the first one, it does also state that you cannot use the same letter more than once, which means the next one would go down to 21. We continue with this trend. The next one's 20, the next one's 19, and the next one is 18. So then, the way to actually write out this equation is 22 factorial, which is just the original number of options we have, over 22, which is, again, the original number, minus the number of terms we are actually using. And we want to make sure to put those in brackets, because otherwise we would come out with a very different answer. So obviously this is equal to 22 factorial over 17 factorial. And if we were to write this out, obviously it would come along to the point where this would come to 17 factorial over 17 factorial, which would basically cancel these ones and make it 22 times 21 all the way to 18. And if we were to actually plug this into our calculator and solve, we would get an answer of 3,160,080 different permutations. However, this is not where this question ends, since it's also implicated with the question above, so we also need to multiply this number by this number, or 90,720 times 316, or 3,160,080, which gives us an answer of 286. I'm not going to even try to pronounce this number because I know I'll just mess it up. What is it? 286,682,457,600. And that's our final answer.